Bismillahirrahmanirrahim. Work done by a variable force. One can plot x component of force versus position. If the force is constant, then this plot becomes a straight line as shown in figure. If the constant force F naught done a work in moving the object from x1 point to the x2 point, then the total work done will be equal to the area under this curve or this shaded area. As we know that the work done is equal to force into displacement, and as in this figure the value of force is actually the width and the value of distance is actually the length of the rectangle. So area of this rectangle will be equal to width into length, and we also know that this area is equal to W, means work. So work is equal to force into displacement, which are the length and width, or we can say that work is actually the area found by this graph. So from this concept we proceed forward that the work done can also be achieved or calculated from the graph by calculating the area under that curve or graph, the graph which consists of or which is plotted by the force versus displacement. So now we want to calculate the total work done by a variable force, not a constant force, as discussed in the previous slide. This figure shows that the path of the particle in xy plane as it moves from point A to point B, the path has been divided into n short intervals of the displacement delta d1, delta d2, and up to so on delta dn. And F1, F2 and Fn are the forces acting during these intervals. So if this path, which is divided into n parts, and a body is moved through this path by applying forces of different magnitudes at different points, and we suppose that there are n forces in n intervals. During each small interval, the force is supposed to be approximately constant. So the work done for the first interval can be calculated or can be written as the dot product of the force vector and the displacement vector. And dot product, we know that the cos component of force into displacement magnitude. F1 dot D can be written as F1 cos of theta 1 into delta D1. Similarly, for the second patch, there will be a work of amount F2 dot delta D2 is equal to F2 cos of theta 2 and delta D2. And by proceeding further, for all the patches, we will get the work done in all the patches individually. To get the total work done in this figure, we will have to sum up all the works in each patch, and then we will get the total work. And from this figure you can see that for the first patch from this point to this point, if we plot graph, then the amount of force, if we say that along y-axis is the amount of force, at F1 is, we suppose that the amount of force is at this value or of this height. If force is more, then height is more, and the body is displaced through a distance d1 or for the first patch, then the total area by this patch will be equal to the work done during this displacement. Similarly, if the force in the second patch is increased to a higher amount or higher level, then the height of the patch will increase. As force is more, the height of the patch describes the force. And the displacement covered in the second patch is supposed to be delta d2. Similarly, in the third patch, the force is further increased to a higher level, and the displacement in the third patch is delta d3, and similarly we move forward for the nth patch. So all patches, the area of all patches represents the work done in each patch. The first patch, area of first patch is the work done, is the amount of work done in the first patch. The area, the magnitude or the value of area of the second patch will be numerically equal to the work done in the second patch. Similarly, in the third patch, the area of the third patch will be numerically equal to the work done in the third patch, and so on. So we want to calculate the total work done. We have to sum up all the areas. The addition of or the sum of all the areas will be equal to total work done performed in this path from A to B by different or variable forces for each patch. So we have calculated the delta W1, mean work done in the first patch, F1 cos of theta 1 delta D1. Similarly, in the second interval, we have calculated the area delta W2, that will be equal to F2 into delta D2, F2 cos of theta 2 delta D2, and so on. And the total work will be equal to delta W1, delta W2, and up to so on delta Wn. And by putting the values of all the works, F1 cos of theta 1 delta D1, F2 cos of theta 2 delta D2, and up to so on Fn cos of theta and delta Dn, we will get the equation 4.2 in the form of sigma or summation form, which represents the total work done. And we have also understood that the total work done will be equal to the area under this curve, or sum of all areas of different patches will be equal to total work done. And if the delta D approaches to 0, or we divide the distances into very small distances or infinitesimally small lengths, then the concept of continuity introduced. And this shows that at every point, if the force is being varied, then it is possible to get the total work done by the concept of integration, as limit delta D approaches to 0 with a sigma sign shows that this is the integration. Derivative integration, differentiation integration concepts are very common and in normal use. So we can replace this term by the sign of integration of f cos of theta delta D1, or we can write in the same way as it is written in 4.3 equation. They are the same concept. So to get the total work done, you use 4.3 equation. So in this limit delta t approaches to 0, the total area of the rectangle shown in the previous figure approaches the area between the f cos of theta curve and the d-axis from A to B as shown in shaded figure. Thus the work done by the variable force in moving a particle between the 2 points is equal to the area under the f cos of theta versus d curve between the 2 points A and B as shown in figure. Okay, next we move to a similar concept and the next topic, which is work done by the gravitational field. Please look at the figure. In figure you see that if a body is moved from A point to B point through this curved path against the gravitational field or against the force of gravity, then we have to do work on that body, or we have to store energy in that body. The energy will be stored in the body in doing work against the gravity. But the total amount of work done in moving from A to B will remain same whether the object is moved from A to B through this path or from any other path, for example from A to D and D to B, or from A to C and C to B. Total work done remains same. The alteration in the path against the gravitational field doesn't change the amount of energy stored or doesn't change the amount of work done for moving the object from A to B point. Now we understand these concepts at this discussion. Let us consider an object of mass m being displaced with a constant velocity from A to B along the various paths in the presence of gravitational field. In this case, the gravitational force is equal to the weight mg of the object. If we want to calculate the work done in each patch, then we have to calculate the work for different scenarios. For example, if we want to calculate the work from A to D and then D to B, and this point is D point, A to D and D to B, then along x-axis, in the direction of x-axis, the total work done will be equal to 0, as we are just moving the mass or pulling the bucket, as we have discussed in the previous lecture, that when the bucket is pulled from some initial position to the final position and no force moves the bucket or pushes the bucket, just we are pulling the bucket upward and we displace it in the horizontal direction, then there will be a total angle of 90 degrees between the upward pull and the displacement. So no work will be done or no energy will be stored in the bucket during the horizontal movement. It means 0 work from A to D. Plus from D to B, as we are moving the object against the gravitational force, we have to apply the force or push the object from lower point to higher point, a D point to B point. So what will be the work? Work will be equal to mg force into displacement h, and cos of angle is 180 as the force is in downward direction, gravity is in downward direction, and we are moving or displacing the object, displacement is in upward direction. So angle is 180 and cos of 180 minus 1. So minus mgh. Mg is the force and h is the displacement. Force into displacement is the total work done, but negative sign is because of the opposite direction of force and displacement. So total work from A to D and D to B will be equal to minus mgh. And if you want to calculate the work done from A to C and C to B, then it will be equal to minus mgh in moving upward direction and 0 in moving horizontal motion from C to B. But if we move in the curved path, we have to divide the whole distance into staircase elements. And we have discussed earlier that total work done will be equal to minus mg into y1 in the first patch. No horizontal work, but in the vertical movement there will be a work mg into y2. Similarly, no work in the horizontal movement, but there will be a work done in the vertical movement during the movement of y3 distance and up to so on. But y1, y plus y2 plus yn, the sum of all these elements is equal to h, as shown here. So total work from A to B will be equal to minus mgh. It means that the work done in the gravitational field is independent of the path, whether the object is moved from A to D, D to B, or A to C and C to B, or directly from A to B. There can be any path, but the work done in the gravitational field remains same. So work done in the gravitational field is independent of the path. The field in which work is zero in a closed path is called conservative field. It means that if from A to B we have to perform work, then from B to A, that amount of work will be retrieved again. Our total work done from A to B and B to again A, total work done will be zero. And this type of field is known as conservative field. We conclude from the above discussion that work done in the Earth's gravitational field is independent of the path followed. And can you prove that the work done along a closed path such as A to C, C to B, B to A, or A, D, B, A in a gravitational field is zero? Yes, we can prove that. The work done in moving in upward direction will be equal to work done moving coming back to that initial position to A will be negative. If one is negative, then other will be positive. The sum of two will be equal to zero. The field in which the work done be independent of the path or followed, or work done in a closed path is zero, is called a conservative field. Thank you for watching the lecture. Please visit the website www.canquality.com for more information, and please subscribe our channel for more informatory and useful lectures. Thank you for watching.